Okay, so yesterday I didn't quite finish these. There was a couple of slides I hadn't quite finished, but I think it's important to actually go through them. So we did get through this one. It said that the way you find the negative of a number in binary is to take what's called the 2's complement of that number in binary. Okay, so what is that 2's complement? Well, the 2's complement is found using a really, really simple process. And that's firstly to take the 1's complement of that number. So in this case, hold on, my laptop seems to have crashed. Woohoo! Yay. Oh, no, not crashed. Just slow. Okay, there we go. Okay, let's see. Yes, my pen is back. Okay, so to find the negative number, you take the 1's complement of that initial number. So here was the number we were using, which was 5 in base 2. Oh, sorry, 5 in base 10. And what we do is we invert all the bits. Okay, so 5 is 0, 1, 0, 1. So if we invert all the bits, we get 1, 0, 1, 0. That's what I mean when I say invert all the bits. You change the 0s to 1s and 1s to 0s. And then we add 1 to the result. Okay, so over here, you've got, here's the 1's complement. You add 1 to it, and the result is called the 2's complement. And the 2's complement represents the negative of the original value. Okay, and you can verify that this satisfies basic maths by adding our positive number, so this is 5, to our negative representation of 5. So 5 plus negative 5, if we add those together and we overflow the leading 1, we end up with 0. You can verify that this works with any number. You invert all the bits, add 1 to it, and those two numbers, when you put them together, will add up to 0. And conversely, if you're given a negative number, and in this case a negative number is represented where the initial bit, the very most significant bit, is a 1, then to figure out what that number is, the magnitude of that number, you need to go and take the 2's complement of that negative number, and that'll give you the magnitude of the original number. Okay? So in this case, we don't know what this number is. There's a 1 in front, so we do know that it is a negative number, but we don't know exactly the magnitude, so you take the 2's complement, and the 2's complement gives you that this number is 19, so the original number represented was negative 19. Okay, now this can get a little bit confusing, because when do we take this first bit as a sign bit that represents a negative or positive number, and when do we take this bit as a part of the magnitude? Okay, it's an issue, because if we said that this bit is part of the magnitude, then this 1, 0, 1, 1, 0, 1 means something totally different to if we interpret this initial bit as a sign bit representing positive or negative. Okay, and the way you get around that is you either tell the person who you're trying to give this number to whether this first bit is a sign bit or not. And what that translates to is, if you've done any programming, who's done some programming? Who's heard of an unsigned integer as opposed to a signed integer? Yeah? So the difference between those is, with an unsigned integer, any number, the first bit of that is representing a magnitude. But with a signed integer, the first bit of that number is representing a sign. Okay? And consequently, this means that unsigned integers cannot be negative. Okay? And signed numbers cannot have as big magnitude as unsigned numbers. Okay, so just to test whether we understand what's going on, let's quickly do these two examples. I'll give you a couple of minutes. So here's a chance for you to figure out how to convert this number What is negative 3 in 4-bit 2's complement notation? Now, the important thing here is the question states 2's complement notation, and that implicitly means that the first bit is a sign bit. Okay, you can't have negative numbers without a sign bit. Okay, so have a go of that. So the process to find what negative 3 is you would find out what 3 is, and then you would take the 2's complement to figure out what negative 3 is. Yep, question? A and D are the same because that is a mistake. Let's get rid of, which one do we want to get rid of, A or D? A, okay, let's get rid of A. If you've already answered A, switch to D. Thank you for picking that up. All right, I'm very encouraged to see that people are not answering C. And why would I be encouraged to see that you're not answering C? Yeah, that's positive 3, right? And also the first bit is a 0, which represents that number represented by C is a positive number. So clearly this negative 3 is not going to be represented by anything which has a 0 at the beginning. But that still leaves you with two choices. Okay, so is that a question or are you pointing at the board? Okay, pointing at the board. Okay, so last chance. Most people have answered. So I'll give you 2 seconds. 1, 0. Okay, so yeah, what is negative 3? It's D. It's A or D. Woohoo! So if you're A or D, that's correct. Okay, because I take the 1's complement of 3, and I was nice enough to give this as positive 3, and you would get 1, 1, 0, 0. I add 1 to that, and I would get 1, 1, 0, 1. Okay? So very good. Okay, so then what about 4.6? What decimal number does 1010, which we are told is in 2's complement notation, represent in decimal? Okay, so quiz opened. Oh, this one does not have as much agreement. Have an argument with your neighbour about what you think it is. It's not B. Why is it not B? Because the leading number, the leading bit, the sign bit is a 1. It's not a 0, right? This leading 1 tells us that this number is negative. So it must be A, C, or D. Well, which one is it? Ooh, I think we have a leader now. All right, I think we're reaching some sort of consensus. Looking good. I can see that you guys are helping each other out. I see answers switching from incorrect to the correct answer. All right. Results now. What is going on with my machine? I apologize for technical difficulties. Oh, I have something. It's back. Okay. Now, what is this? And the answer is, which one am I doing? This one. The answer is A, is what people think. But is that correct? Okay, so 1010. What is the process by which we take to figure out the magnitude of this? We know it's negative. So we take the 2's complement of this number to give us the magnitude. So the 2's complement we find by inverting the bits, giving us the 1's complement, which will give us 0, 1, 0, 1. And then we add 1 to it to give us the 2's complement. This gives us 0, 1, 1, 0. So that's the 2's comp. Right? And 0, 1, 1, 0 is equal to 6. And therefore this number represents minus 6. Well done. Okay. Hopefully, at least you've tried, if you're in this class, you'll have tried this question at least once, which is what we hope for. Okay, so then the process of subtraction becomes really easy. Let's say I wish to subtract 35 from 60 using 7-bit signed binary. This means the most significant bit is a sign bit. Then, how do we do this? Well, you figure out that I want to subtract 35 from 60, so that means it's 60 minus 35. And mathematically, this is equivalent to saying it's 60 plus minus 35. And we know this equals 25. So, what do? Well, we have 60 and we have 35, which we know is in 7-bit signed binary, and it just so happens that this 7th bit is enough to give us a sign, and these 6 bits are enough to give us a magnitude up to 63. Okay? So, to work out this problem, you need to find minus 35. To do that, you complement each one of the bits, giving us the 1's complement. Right? So here's 35. You need to find the 1's complement. And then you need to add 1 to it to give us minus 35. Okay? So now we can add the positive number 60 to the negative number 35 to give us positive 25. And it would be good if we checked that this actually worked. Okay, so over here you've got minus 35 plus 60, so I'm just taking this number here putting it up below here, and we're saying if we add them together, so let's do that. 1 plus 0 gives us 1. The zeros here gives us 0. 1 plus 1 gives us 0. Carry the 1. 1 plus 1 plus 1 gives us 1 here. Carry the 1. And then if I go 1 plus 1, I get 0. And we carry the 1. And this 1 plus 1 here gives us 0. And we would have an overflowed 1 here. All right? So now if we look at this number and interpret it, you would see that the sign bit means this is positive. And if we add up these bits here, this would be 2 to the 4 plus 2 to the 3 plus 2 to the 0, which is 16 plus 8 plus 1 equals 25. Okay? Now, just so what happens if you get a result and this number is a 1? Well, you would know you have a negative number, and to figure out what that negative number is, you need to do the process that we had on the previous slide. You find the 2's complement to find the magnitude. Okay, that's pretty much it for this part. This table is a really good summary of what we have learned about unsigned and signed numbers. Okay, in this particular example, I've used only 4 bits just to make it easier to read. And if you study this, then note that some parts of some numbers cannot be represented by certain schemes of whether something is signed or unsigned. Okay, so really keep that in mind, because this really affects how you do arithmetic in digital systems. Okay, so if you specify an unsigned integer as a variable in programming and you try to assign it a negative value, it'll work, but the value you assign it won't be what you think it will be. And I won't go into it, but that's something that you'll come across, and you'll do programming regardless of what stream of engineering you do decide to go into. Okay, so please have a look at this table when you study for the mid-semester test and your exam hint. Okay, so that's that. And now let's move on to 2 and 3 input logic gates. So this is pretty straightforward stuff. In fact, it's so straightforward that let's have a 2-minute break. Okay, so I think we can afford to let the brain digest what we saw in the previous section for a second. All right, let's get back to it. Okay, so these components are the basic building blocks of any digital circuit. So just like when you're building an analog circuit, you've got components, you've got resistors, voltage sources, you've got current sources, you'll have capacitors, capacitors, inductors, and op amps. Well, in digital circuits, you have what we call logic gates. Here's an example of logic gate. Okay, so you will be able to recognize and combine basic logic gates into logic functions by the end of this. And you'll be able to turn a bunch of logic gates that you see on a page into a truth table, and you'll be able to prove the equality of some simple functions using truth tables. Okay, so here are the three most basic gates that you would use in any digital circuit. And in fact, using just these three gates, you can make any digital circuit. You can make a full Intel CPU if you wanted to. You would need a lot of them, billions and billions and billions of them, and it would be really, really inefficient, but you can do it. In fact, if you do continue on in ECSE, in second year you'll learn how to do this in a simulator, and in third year you would actually build yourself a small microprocessor, small CPU, and run some commands on that. Okay, so the good thing about these things is that they are memoryless, which means that the output only depends on what the current inputs are. So if the current inputs, for example, are 2 1s on this AND gate, the output would give you a 1. And as soon as this changes, well, the output changes as well. That's not strictly true because there is some minute lag time between when an input changes and when an output changes, and that's called the propagation delay. And you can look on that. Look on the spec sheets on your NAND gates to find that propagation delay that you've got in your kits. Okay, so these circuits can be used to make many different things, such as adders. Adders, unsurprisingly, add binary digits together. You can make memory decoders and multiplexers. So a decoder gives you a specific output depending on the combination of inputs you give in for any arbitrary function, and multiplexers help you to select different inputs depending on another input. Logic gates, as you may or may not know, they're available in simple chips. You've got a bunch of NAND gates on one of the chips that you have, and you can make logic functions by connecting the inputs and outputs of those. But nowadays, computers are so complicated that we often don't use simple logic, individual logic gates and connect together. We use field programmable gate arrays, or what we call FPGAs. So these things are large numbers of gates and logic all located in one area, and using software, you program connections between them. Okay? So you would program this gate connects to this gate, connects to this gate, connects back to this gate to give us whatever, some sort of output and input. And that's how a lot of rapid construction of logic circuits happens these days. Okay, so one of the first and easiest gates is the AND gate. The AND gate is given by this symbol, which importantly has a flat side, okay, and a rounded front. Okay, so that shape is important. If you get the shape wrong, it might be interpreted as a different gate. Or if it's really wrong, not even a gate that anyone has created or anyone has invented before. If we so the behavior of this gate can be summarized by a truth table. And truth tables exist for all of the gates that we look at. A truth table tells us what the output, in this case F, should be if we provide it with a specific combination of inputs, A and B here. Now, because we're working with digital circuits, these inputs can only be high or low voltages, right? So a voltage high could be 5 volts, voltage low would be 0 volts, for example. And similarly, the output can only be high or low. So it's convenient to represent what these inputs and outputs could be by zeros and ones. Now, here's the behavior of the AND gate. It says that the output is a 1 if and only if A is a 1 and B is a 1. And that's why it's called an AND gate. Okay, so the truth table here illustrates that. So if I have a 0 for A, a 0 for B, then the output of the AND gate will be a 0. If I have a 0 for either of the inputs, A or B, then the output is 0. And the output is 1 if and only if A is equal to 1 and B is equal to 1. And that's why it's called an AND gate. Okay. So, also one thing to note, as the order of inputs for these gates have no effect. So that's illustrated in this table. So if I shifted, in these two lines, doesn't matter which one of these is a 1, or doesn't matter which one of these is a 0. If either of these is a 0, then the output is a 0. So for an AND gate, the order of inputs has no effect. Okay. So here are some shortcuts when you're thinking about AND gates. If I put the same input into an AND gate, so if I have A as an input and this is a connection between what the input here is and into the other input. So if I have A and A, and also an AND function in notation is usually represented by either a dot for multiplication, or you simply omit the dot. So it could be AA, because that's multiplication, and that's a good shortcut for what an AND gate looks like. So if you put A and A together, this means that if A is a 0, then the output's going to be a 0, and if A is a 1, then the output is going to be a 1. And some other shortcuts, any input ANDed with a 0, okay, so A could be a 0 or a 1, doesn't matter. If I have a 0 on any other input on the AND gate, then the output will always be 0. That's represented by these two rows. If I have a 1 on the other terminal, depending on what A is, the output will always just be whatever A is. Okay? Now these are useful shortcuts that will come in handy later. What happens, can you have AND gates which have greater than 2 inputs? Yes, you can. Here's an example of a 3-input AND gate, and as you might imagine, we can write a truth table for this. Here's an easy way to do it. Okay, and so for a truth table, you need to list all the possible combinations of the inputs. So because there are 3 inputs, this means there are 2 to the 3 possible combinations, which means there are 8 possible combinations here. 8 combinations. Right? Okay, so as you might imagine, for a 3-input AND gate, the output is a 1 if and only if A is a 1, B is a 1, and C is a 1. So A and B and C. Okay, so that's this row here. This row here. And so the truth table would look like this. 0, 0, 0, 0, 0, 0, 0, 0, 1. Okay? So that's what. So you can imagine what a 4-input AND gate would look like. It'd be all zeros except when A and B and C and whatever the 4th variable is, D is equal to 1. Okay. What happens if I cascade AND gates? Well, if I take A and B and take its output and stick it into another AND gate, then I get, well, the first part, this would give me A and B, which is this part, and then the second gate would give me A and B and C. Well, this is all equivalent to just a 3-input AND gate. They're all the same, no matter which way you slice and dice it. I could do B and C first, and I could then AND that with the A, and this would all give me A, B, and A, B, C. So in actual fact, these brackets can disappear in much the same way as you do with normal algebra. So in normal algebra, if I saw A, B times C, well, you could expand that out to A, B, C. We know that, and that's equal to A, B, C. So this is the case in normal algebra. This is what we call Boolean algebra. So I won't do the truth table, but we can prove that quite easily using the truth table. Okay, so here's the second type of gate that you need to be familiar with. It's called the NOT gate. or it's called an inverter. Okay, now the inverter, the most important part of the drawing of the inverter is this little bubble here. Okay? This little bubble means take whatever the input is on the left of the bubble and whatever it is, invert it, turn it into the opposite of what it is. If it's a 1, turn it into a 0. If it's a 0, it turns into a 1. Okay, so that's what this that's what this little bubble means. There's a triangle here because it's not really very good to do that for a circuit because that's really hard to see. Okay, so that's why we have this triangle here. Okay, because it clearly marks that there is a gate there and the output is inverted. Okay, so the truth table for that is really simple. Whatever the input is, the output F is the opposite. If it's a 0, it's a 1. A is 0, F is 1. A is 1, F is 0. Okay, so that's the second type of gate. And the last type of gate is the OR gate. Okay, now this is, so to draw an OR gate, the OR gate does not have a flat back. It's got a curved back. Okay, as you can see here. I'm exaggerating it a bit with the line. And the OR gate comes to a pointy bit at the front, and it's a curved pointy bit. Okay? So make sure when you draw an OR gate, you have these details correct. Now, the output of an OR gate is represented as A or B, and OR is always represented with a plus sign. Okay? A plus sign means in terms of Boolean or logic gate algebra, it means OR. So this here means A or B. Okay, that's what these things mean. Now, the truth table for an OR gate. Truth table for an OR gate is different to the AND gate, but the name of the gate makes sense because you'll see that the output is 1, F equals 1, when A equals 1 or B equals 1. So when either of these is equal to 1, the output is equal to 1. So the only time the OR gate gives a 0 is when A is 0 and B is 0. Okay? That's the only row that gives a 0. Okay. So similar to the AND gate, there are some shortcuts. If you put A into both input terminals of an OR gate, you will get out A. So whatever A is here, if it's 0 or 1, well, the output will be correspondingly the same value as what you put in. If you put in a 0 into one of the terminals, it has no effect. It just makes the gate become A. The output will just be totally reliant on A. And the other interesting shortcut is that if I put a 1 into an OR gate, the output will always be 1, regardless of what A is. Okay, so these are useful because, let's just say you have a chip which has a number of OR gates on it, but you don't want to you want to use all of the gates, but not all of them want to be used for the same function. You don't want to use an OR for every function. Sometimes you might just want to pass a value A through a gate just because you might want to use the propagation, you might want to use the slight time lag. The slight time lag here to give us an output, and even though it hasn't actually changed the input. So, yes. What happens if you've got more than 2 inputs? Well, in that case, let's do a truth table for this. So if you see the way I'm drawing the truth table, it's really quick to write. If you do a whole load of 0s, 1s, and then you start halving the numbers of 0, 1 switches, that helps you to draw the truth table pretty quickly, rather than going 0, 0, 0, 0, 0, 1, 0, 1, 0, etc. Try it yourself, you'll find it's faster. The output will be a 1 when A is 1, or B is 1, or C is 1. So it'll be 0, and you'll get 1s for the rest. Okay, so F equals 1 when A equals 1, or B equals 1, or C equals 1. That's what the OR gate does. So you can extend that to 4 gates, 4 inputs, 5 inputs, however many inputs. Okay, so same thing with OR gates if you cascade them. So if you put one after another, well, if I did this, this would be A or B in brackets, and then if the output of this gate would be A or B or C, and you can actually get rid of the brackets here, just like in normal algebra, and the output would be A or B or C. And that works regardless of how you switch these OR gates around. They all serve exactly the same function. All right. So using these 3 gates, you can construct any logical function that we can think of. How does that become useful? Well, I'll show you. So over here, well, I'll show you later on, but we've got to do a little bit of groundwork before we get to that point. We can start to combine a number of gates together. We don't have to just combine OR gates with OR gates and AND gates with AND gates. We can start mixing them up. So over here, you can mix up an OR gate here with an AND gate here. And what happens is you get B or C as the output of this gate, and which becomes the input of the AND gate, and the output here becomes F equals A and, in brackets, B or B plus C. Over here, you could use 2 AND gates and an OR gate here, and what would you get? You'd get the output of this being what? What would the output of this gate be? The top gate. A and B. Yeah. And the output of the bottom gate. So I've got, in the bottom gate, I've got A going into this one, and I've got C in the bottom, so this would be A and C. And the output of this gate would then correspondingly be whatever the inputs on the OR gates are. So it'd be A and B, or A and C. Now, it may not be clear just from looking at the 2 functions here, or looking at the arrangement of the gates, but these 2 are exactly the same. Okay? So this A, B, or C, this function f at the top and this function f at the bottom, they're exactly the same. How do we prove this, though? And the way to prove this is we can use a truth table. So we've used truth tables to define what the gates do. We can do it the other way around. We can get a truth table from an arrangement of gates. Okay, so here's an example. So for all possible combinations of A, B, and C, so over here, let's do all possible combinations. So when you're asked to prove whether 2 arrangements of gates or functions are equivalent, you can use a truth table to prove this. So over here, you can go B or C. So B or C, given the values in the columns, you can say B or C is 0, 1, 1, 1, 0, 1, 1, 1. Over here, you've got A and B in this column. So these are just taken directly from the gates that I've shown here. So you've got B and C, you've got A, blah, blah, blah. Okay, so you've got A and B. So A and B, we have to look at the A and B columns. So you get 0, 0, 0, 0, 0, 0, 1, 1. Am I right? Okay. What about AC? A and C here would give me what? 0 then, 0 then, 0 then, 0 then, 0 then, 1 then, 0 then. Very good. Great. So now, what is A and B or C? So now you've got B or C here, and you've got A here. So what we need to do is look at these two columns and perform an AND operation between them, right? So what is A and B or C for this row? 0, 0, 0, 0, 0, 1, 1, 1. And finally, we look at these two and we OR them together. So we've got A and B or A and C, right? So let's OR them together. So looking at these two columns, what's this one? 0, 0, 0, 0, 0, 1, 1, and 1. Oops. Okay? So as long as the outputs are exactly the same between two logic functions or arrangements of gates, hopefully you can see that gates becomes a function, becomes a truth table. As long as you can prove that the outputs are exactly the same between these two, then we can say that these two functions are exactly the same. Okay? And that's how you prove equivalence of two sets of gates and two sets of functions. All right, so here's where we'll finish off. Have a go, do this for me. And give me whether this is A, B, or C. All right, some people have worked ahead and they've already done it. Great. Okay, so the process you need to have a look at is what is the output of the gates from left to right, and how do they combine to give us the output F. Okay, I think this is good. I think you'll pretty much have a handle on all this material, which is great. All right, if you want to be recording the system, you've got about 5 seconds. 4, 3, 2, 1. All right. What is the answer? Let's have a look. It is 5.7. A is what people think. All right, so what is the output of this gate? A and B. The output of this gate is B or C. The output of this gate is A and B, which I didn't mention before. The inversion can be given as that. And the output here will be AB prime times B plus C. Thanks very much. See you next